Okay, welcome to the third video lecture that I've put together to complement the material I've been delivering in the main lectures for the EG168 module, Engineering, Scientific and Engineering Skills, Level 1 at Swansea University. And what we're going to look at today is some of the basic dynamics going on in the horizontal motion of the Bloodhound vehicle, because this forms the basis for the computer program that you should be currently working with to complete your final assignment. The program is written in MATLAB, and I'm sure some of you have started exploring what is going on inside this program, particularly in the Calculate Mission Profiles function. And this short video will hopefully help you understand what is going on inside that program. I'm going to start off by attempting to draw a sketch of the vehicle. So first of all, this is the ground that the car is running over, and of course Bloodhound has 4 wheels. This is going to be a side sketch of the car. So this is the nose, and down to the back of the car. There's a big fin at the back for lateral stability, an intake duct here, a cockpit, and then a nice pointy nose. Now, of course, for this car to be accelerated forwards, it needs thrust. Okay, so the thrust line of the car roughly sits there. But of course, opposing the motion of the car is a drag force. So we don't know exactly where on the car the center of line of that force is going to act, but it's going to be opposing the thrust in some way. We also know what makes up these two forces. So we know that the car has 2 engines. It has an EG200 jet engine, generating about 9 tons of thrust. It also has a rocket generating slightly more thrust than the jet engine. So these two components together comprise the thrust that is accelerating the car forward. And the drag has multiple components too. There's the air resistance. There is the rolling resistance. That's the actual friction between the car and the ground at the wheels. And within the bearings that are allowing the wheels to rotate. And also when the car is slowing down, we're trying to increase this drag value by using parachutes and air brakes. And if you go into the set parameters M file that is attached to the code, you will see values for all of these variables here, and importantly you will see how these things vary with speed or with Mach number. Now, of course, if we assume that the car is travelling, in this case, from right to left, and we'll make right to left the positive displacement direction, we can then write that the thrust minus the drag is equal to the net force F acting upon the car. And of course, if the car is accelerating, this net force F should be positive for acceleration. If it is negative, the car is decelerating. So if the drag is greater than the thrust, then the car will be decelerating. And we all should know that we can write Newton's second law in the following form. So Newton's second law, which essentially states that the net force acting on a body is always equal to its rate of change of momentum, but we can write that in a simplified form as F equals ma, which is often the way that it gets taught, and you will memorize it in school, where F is the net force acting on the body, in our case the car, m is the mass of the car, and a is the acceleration. Well, of course, if we know the thrust from the engines and we know the drag, or at least we can estimate what the drag of the car is going to be at any given speed, we can work out what the force is going to be. We also know what the mass of the car is, and we know how this changes over time as it burns fuel, so we can work out the acceleration. And the first thing that happens in the MATLAB program that you get is that the acceleration against time function is calculated so that you can plot a graph of acceleration against time simply by using this equation here. Now we also know that we can write acceleration as rate of change of velocity. So we can express that in this form, dv by dt, or the rate of change of velocity. And if we rearrange this, so we have f dt equals m dv, and then we integrate. Then in principle, if we know what this f function looks like, and we know what the mass of the car is doing, then we can compute those two integrals there. So how does the MATLAB program do this? Well, let's take the integral on the left-hand side as an example. So let's take this integral here. Now, rather than compute that integral analytically, the program must do what's known as a numerical integration of that integral. So let's just have a think about how that works. If we know how this force is varying with time, then essentially that integral there, if this is t and this is f, and we know the force at t1, and we know what that force is at some small time interval later, dt, and this dt here is actually the dt that gets set right at the start of the program. It's the size of the time step in the numerical scheme. Then this integral here is simply the area underneath this curve. If you draw a straight line between the value of the force at t1 and the value of the force at t2, that integral is simply the area under this curve. So if we assume that we can compute this integral here, and we also make the assumption that the mass of the car essentially is constant across this very small time step here, then essentially we can work out what the change in velocity would be across that time step. So we're now in a position to be able to work out how the velocity of the car is changing time step by time step. And that's the second thing that the program plots. It plots a graph of velocity against time. So we now have essentially we have a function for the velocity as a function of time, and of course velocity is simply rate of change of displacement. And if we integrate this equation, again using a numerical method which is embedded within that calculate mission profiles routine, then we can not only compute how the velocity is changing with each time step, but we can also compute how much the car is moving with each time step. So that's essentially the mathematics that's going on behind the algorithm that you find in the program that you've been given to play with for your final assignment. You don't necessarily need to be able to understand everything that I've explained here and how that translates into MATLAB code, but hopefully this will give you some idea of what's going on in terms of the theory behind the program. But it all simply boils down to, do we know Do we know what the thrust looks like as the speed of the car varies? Do we know what the drag looks like as the speed of the car varies? And can we build up the components of this equation here, which is Newton's second law, and solve it? That's what's going on in the background while you're running that program.